absolute convergence versus conditional convergence. What does that mean? Okay. Let me give you an example of the series that's absolutely convergent. Let's say that's n plus 1 over n squared. Okay, I'm going to write this thing out. So this is 1 over 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared and dot, dot, dot. You know what I'm saying? Okay, now, is this series from hunch, let's say, if you don't know the definition of these terms yet, is this absolutely convergent or is it conditionally convergent is the question.
Absolutely convergent.
Absolutely. What makes you say this is absolutely convergent from that word absolute?
The absolute values, the 1 over n squared p series.
Absolute convergence means if we take absolute value around, oh, that's a bad idea because I have minus sign, but you know what I'm saying. If we convert all of these minus signs to plus sign, because alternating, this is still an alternating series. Alternating series have a lot easier time converging than other series. You know what I'm saying? Because that negative signs tend to cancel each other, so these things fluctuate back and forth, right? So if we convert all of this minus sign to plus sign, in other words, take absolute value of every single term, you put absolute value here, you get it? Would that still converge? If you do, this just becomes a p-series with a p-value 2. So this will still converge. You know what I'm saying? Even if it's alternating. Then we say this series is absolutely convergent. Did that make sense to you? Okay, let me give you a counter example of something that is not absolutely convergent. Okay, this is called the conditionally convergent, and this is yesterday's example. Okay, negative 1 to n plus 1 over n. Remember this guy? This was 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, dot, 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 dot. Okay, now if you do an absolute convergence test, meaning get rid of this minus alternating sign and put an absolute value around it, then this becomes a harmonic series. P is equal to 1 and this thing diverges. Good. So only thing that is making this series convergent is because of the alternating signs, correct? They help you a lot. Because alternating series, it only the sequence needs to die down to 0. And then of course, strictly decreasing, but come on, for all our purposes, this is strictly decreasing, right? So here's the definition. Conditional convergence is if it's not absolutely convergent, this is the key. I'm gonna highlight it. Not absolutely convergent, but convergent anyway due to alternating signs. You get it? And this not absolutely convergent is the key here. Good. Okay, now here's a theorem of mathematicians. In case the series is convergent absolutely, then it is convergent. In case that was not clear before. If statement is true absolutely, then it's true. And I'm thinking, wow, only mathematicians come up with such a thing. You have to make a theorem about that? But sure enough, many students mess this up. Okay, here's a question for you. Typically, this type of question shows up a lot. Determine if the given series is at A on a 1, absolutely convergent, 2, conditionally convergent, or 3, divergent. And let's say you have absolute convergence test. Absolute convergence test meaning you take away all the negative signs and treat it as a regular series, right? And you have an alternating series test, right? Which test should you conduct first?
Alternating, absolutely convergent test.
Absolutely, right? Many students will do an alternating series test first. And so for something like this, if you do an alternating series test, it'll converge, right? It should, because this thing, if you take a limit of 1 over n squared, that becomes 0. And they will conclude, oh, this is conditionally convergent. No. You still don't know whether this is absolutely convergent or not. Because you look at the definition, this highlighted, this part, this biggie. You have to show that this is not absolutely convergent, and then by alternating series test is convergent, right? This part. Then alternating series test. You have to do both. So you still need to do absolute convergence test anyway. However, if you do absolute convergence test first, and if it's convergent, it'll definitely pass the alternating series test too. So you don't have to bother, you just stop and say it's absolutely convergent. You don't have to do second test. You know what I'm saying? You see the logic? Oh, yeah, whenever I give a test, many students do it backward. Okay, and if it fails both, then it's divergent. You get it? So this theorem exists for a reason, okay? When you do an absolute series convergence test, and if it passes, you stop. Don't waste your time doing alternating series tests. It'll converge too, okay? So absolute series test is a trump. Oh, I didn't mean the name Trump, but you know, it trumps everything. You get it? These days, you cannot even use this thing. Okay. Do you know where the term trump comes from? There's a card game called Bridge, and there's a trump card. One of the suit is a trump, which trumps over other. Oh, okay, whatever. That's where it came from, okay? Now, then, here's something called the ratio test. This is an absolute convergence test, okay? What you do is you take a ratio of the current term and the next term and take a limit as in, so it's kind of like L'Hopital possibly thingy. And if that thing is less than 1, then it's absolutely convergent. If that thing is greater than 1, then this is divergent. Absolutely. Oh, at least not absolutely convergent. And if this is equal to 1, and then actually in this case it's divergent anyway. Don't bother with alternating series test. It'll grow. It doesn't die down. And if it's equal to 1, we don't know. Okay. Instead of giving you the theory on this, I'll actually give you the example first, so this becomes concrete, okay? Because usually I do it like that because students have seen that ratio test first. But, well, yeah, let's do this one. Okay? And to see, many times you have something that looks like that and it's factorial. This is a headache because you cannot differentiate, you cannot integrate factorial. I mean, when it comes to factorial, what do? Our skills are very limited when you're up against the factorial. But ratio test is the one that shines, okay? So this is how the ratio test is done. You take a limit as n approaches infinity and you put an absolute value around it. And then you take this thingy and put it in the denominator. You with me? And then on the numerator, you put the very next term. You get it? Do you see how to at least put it? And I'm going to convince you why this works, okay? Okay, then here comes the challenging part. Fraction simplification. You right? Well, let's get rid of the factorial first. Do you agree between the factorials? Do you at least agree? Then this thingy, the top one, let's just think about it. We have this thingy, right? You with me? Okay. Do you see one of this thing cancels that thing? Okay, then what do you have left? Let's just look at what we have left. That's n power, and so what we have is this. Are we good? Are we good? Do you remember this from chapter 8? This, as n approaches infinity, what is this, right?
E.
Okay. It's this thingy, isn't it? Oh, E. Do you remember E? Yeah, this is E. Okay, let's review. Giant E, followed by ln, and then n plus 1 over n to the n power, but then n can come into the front, correct? Okay, let's check. So this thing becomes 1, so it's ln 1, so this whole thing approaches 0 times infinity. So we tweak it a little more. So we write it like this, e to d ln n plus 1 over n over 1 over n. Eh? Say yes.
Yes.
Okay, now L'Hopitalise. Okay, I'll do the denominator, you guys do the numerator, all right? Okay, I'm done. What do you have? I think it would have been better if we converted it into this thing, right? Split the fraction. That's easier to see. Okay. Now what do you have? Take that thing into the denominator. So we have 1 plus 1 over n, and then derivative, the chain rule, which is same thing as this. Oh my God, that's a lot of, let me move that thing out. This is gigantic fraction. Do you see it? Oh, the negative one didn't get moved. Do you see it? You with me? Okay, then. So this thingy cancels this thingy, doesn't it? So what you have left is limit of n approaching infinity of e to d 1 over 1 plus 1 over n. Eh? Say yes. Now we can take the limit, and this thingy approaches 0 right there. So this is e. Now here's the thing, e is more than 1, right? 2.72-ish, which means according to our ratio test, this thing diverges. You get it? Our series is divergent. Is how you conclude this. We really did not need this, because if you think about it, factorial versus n to the n power, which one grows faster? The top one grows faster. You know what I'm saying? So this sequence inside does not even converge to 0. So obviously this will diverge, but I wanted you to see how the ratio test is being used, okay? You take a ratio and factorials cancel very nice on the ratio test, you get it? And many other things. So here's a ratio test idea. Why does it work? Okay, here's an idea. Say if you take a ratio, meaning limit of, let's say just an plus 1 over an. This is a ratio test, n approaching infinity, right? Let's say this is equal to L, some limit, and that may or may not be less than 1, okay? Okay, then what that means is this ratio an plus 1 over an, absolute value, this is approximately equal to n for some large n, right? Because n approaches infinity and these two becomes about 1. That makes sense to you? Because the concept of a limit, n gets really, really big. What that means is an plus 1 is approximately equal to an times L for large n. That makes sense to you? Say yes. Who's confused? If you're confused, now is the time. Okay, that looks like recursive formula of geometric series to you. So after so many thousands and thousands of terms, eventually it's going to mimic this. Let's say k, n, k, k, right? And the next term is then ak times L, you get it? Approximately. And the next term is you multiply another L. That mimics geometric series now, doesn't it? Eventually, after so many thousands of terms. What was the criteria for geometric series convergence? When does the geometric series converge?
Absolute value of r is less than 1.
Absolutely. In this case, L acts as our common ratio r. So if this thingy is less than 1, you get it? Well, absolute value. Because we already took the absolute value, so we know L is positive. You know what I'm saying? Huh. So this works kind of like geometric series. Eventually, if the ratio test gives you a finite number, what that means is after so many thousands of terms, this thing will eventually mimic geometric series. You get it? Okay, well, there's a thing called the root test. Root test is not in your book, but I always felt that this is important. Actually, when you take analyst in college, root test is more important. Okay, everything starts from root test and you use the root test to prove the ratio test. Okay, so here's root test. And it's not a proof according to analysts, but it's a convincing argument, just like ratio test argument. It's about the same idea. So you take nth root of absolute value of an, and you get some kind of limit. And it depends on whether that thing is greater than 1 or less than 1. Okay, what that means is this thingy is approximately equal to L for large n, right? That's what limit means, infinity. And then what that means is we'll take nth power on both sides, right, for large n. Oh, this is even better. This looks like explicit formula for geometric series now, doesn't it? So after so many thousands of terms, eventually it's going to look like this. And the next one will look like this. And the next one will look like this. That still mimics geometric series now, doesn't it? So this thing is absolutely convergent if and only if L is strictly less than 1. Okay, here's a couple of caution. Nth root test, you only use it if your entire series looks like this, something to the nth power. Then you take an nth root, and it's such a convenient thing to do, right? Otherwise, when in doubt, go with the ratio test. Even if it looks like that, if you take a ratio test, it still works. So ratio test is usually the way to go, but there are like few test cases, and of course, nth root test is more important in analysis. So I thought you should know it, but you can usually, ratio test will do the job. And then you are saying, well, what about when it's equal to 1? In case of geometric series, equal to 1 was divergent now, wasn't it? Wasn't it? So why do we say this is inconclusive here, right? In this case, it doesn't exactly mimic geometric series. Let me give you an example, okay? Take this as an example, our favorite alternating series. Let's do a ratio test, shall we? Limit of n approaching infinity of, we can just do this and lose the alternating sign thingy because we're taking absolute value anyway, right? Let's make our life easier. Good. Too much algebra, or can you simplify a fraction like that? Good. We got 1. Well, in case of geometric series, this is divergent. If the common ratio is equal to 1, then it's divergent series. But lo and behold, we have seen this harmonic alternating series before, right? This thing is in fact convergent, isn't it? Due to alternating series test. So in this case, this is convergent and we got 1. But hey, look at this now. If you do the ratio test, it'll give you exactly the same thing, right? And you get 1, but this is divergent series now, isn't it? So when you get 1 from ratio test, it can go either way. And then the reason it goes either way is because of the alternating series tests. Sometimes they converge. So ratio test alone does not tell you anything. So you have to do some other tests, such as an integral test or alternating series test. You get it? So when it's equal to 1, it's inconclusive. And then here's a funny thing. Many students on the test, you first do a ratio test, like I told you to, and you get 1. Okay, that didn't work, right? And let's try the root test. If you do a root test, guess what you're gonna get? It also gives you 1. They're the same thing. They always give you exactly the same results, so don't bother. You only need to do one of the two. Okay, in analysis, there are little tiny weird cases where the root test will work and ratio test will fail. You'll never see that case. Okay, I got a degree in math without seeing that exception. Okay, so it's like, don't worry, you'll never see it. And you probably, unless you pursue PhD in math, you will never see it. So for your purpose, ratio test and root test are the same thing. And in analysis, people prove the root test rigorously, and they use that to prove the ratio test anyway. Okay, let's try ratio test first because we don't know any better, right? Okay, so let's try the ratio test. Limit, Let's try the ratio test again. Limit as n approaching infinity. And then you put 1 over n, ln n. So here you put 1 over n plus 1, ln n plus 1, like that, eh? Okay. Let's see how that thing simplifies. And that thing, of course, simplifies like this. And on the Dropbox note, I think I screwed up. Well, I just did something else, but this makes more sense. N plus 1, and then ln n plus 1. You with me so far? Okay, now this is infinity over infinity, isn't it? So we L'Hospitalize it. Once you do that, I'll do the numerator and you guys do the denominator. It's a product rule, so u prime 1 times v ln n plus n times 1 over n. You know what I'm saying? Oh, that's 1. That's nice, isn't it? What do you have for the denominator?
Is it ln n plus 1 parenthesis plus 1? Yeah.
Yeah, like
n plus 1 over 1 n plus 1.
Okay. Well, that's still infinity over infinity. L'Hospitalize it one more. Round 2. So this becomes 1 over n over, and this becomes 1 over n plus 1, eh? Say yes. And that thingy, of course, is 1. And those of you who are weak in algebra, right, now that's 1, eh? Whoops, inconclusive. That thingy didn't work, right? So we say, oh, that failed. Shall we try integral test now? Yeah, let's try integral test. So change the tactic. So integral test, we have 1 over, still absolute value of it, right? And we are comparing it with this integral now. And we'll decide this lower limit later, but x ln x, right? Dx, if you will, like that, infinity. Depend on where we want to put 1 here or 2 here, depends on the direction of the inequality. Right, because if it's just a 1 over n, it'll diverge. 1 over n squared will converge, but we have 1 over n times ln n. Does ln help this? It'll help a little bit, but does it help enough to make this converge? We don't know. I guess we are integrating separately, right? Because this one takes some kind of integrity, so we'll do that here. So this is the integrity part. Dx over x ln x. U is equal to ln x. Du is equal to 1 over x dx, eh? Do you see that? So this is du over u, eh? Y'all with me? Still remember? U substitution. Okay, and this is ln, and we are sure, right? Because if you're not, don't write it. Negative 10-point rule still applies. I should say negative 10% rule, because it's like 10 point is a lot more than 10%. Okay, so come back here now. So this thingy is equal to limit of b approaching infinity of something to b, something to be, I'm still not sure what that something is, dx over x ln x, and then limit b approaching infinity of that thingy, right, ln. Oh yeah, I have to finish the integral now, don't I? ln x. Yeah, there is such thing, ln x. Okay. So ln x. 1 or 2 to the, oh, we know this is divergent, so let's put 1, right? Oh no, let's put 2. What am I saying? We should put 2. This is 2. Same thing in that way. You know what I'm saying? You do know that these two needs to be exactly the same thing, right? If inequality is pointing that way, or you want me to draw few rectangles for you? If you want to see the rectangles, show your virtual hands. Okay, so, okay, I'm gonna draw the rectangles. Minus, I open the absolute value and close the parenthesis. Minus ln 2. Good. And this is infinity. Okay, here comes the rectangles. I guess I'll draw them here. Say this function, it's got to look like this, right? 1 over x times ln x. And we want, this thing is at that area starting from 1 right here. This is infinity. So in order to make this thing a fair comparison, we have to draw the rectangle like this. Oh, I screwed up. This is not 1, this is 2. Because this thing starts from 2. This is rectangle number 2, and this is rectangle number 3. You know what I'm saying? That's 4. So you see why we have to have a same starting index. You good? Okay, so this thingy diverged. So it just failed the absolute convergence test. You know what I'm saying? You know what I'm saying? Because our original series was this alternating series, but I have taken an absolute value of it, so this is still absolute convergence test. You with me? So conclusion here is good. Now we move on to alternating series tests. You don't have to write this title. Okay, let's do that. So number 1, we have to say limit, oh, not b, n, approaching infinity of our bn, which is 1 over n ln n, right? Well, that's definitely 0, so that one checks out. Number 2, it needs to be strictly less than the previous one, strictly decreasing series, and that is, and you do have to write the symbol, our deduct points. That thingy has to be strictly less than 1 over n ln n a. Cross multiply. So n ln n less than or equal to n plus 1 ln n plus 1 a. Oh, this is true for all n now, isn't it? Yeah, that definitely is true. So now the conclusion. Conditionally convergent. You get it? This is what it required. What is required to show conditional convergence? Let's review. You have to have not absolutely convergent and alternating series passes. You get it? Okay. Any questions before I go to 26? Okay.
Yes, sorry.
Yes. It's okay.
Sorry, we don't need to say like for all n that's positive, right? We can just, since we already assume n starts at 2, right?
Yeah, we don't have to say. I mean, it's still true for all n, right? Even if n is negative, that's still true, right?
I mean, if n is negative ln, n just doesn't exist.
I know, but that statement is, oh yeah, I guess. I mean, it's like, oh, it's my habit to write these things, but you don't have to. That's why I didn't want to write it, but I always just write down the starting index right there. If I'm writing this myself personally, that's what I do. But that's kind of misleading. If I write it, then students will have to wonder, why do we have to write it? You know what I'm saying?
Okay, but you do want us to write the arrow symbol on two sides, right?
This is a requirement. This is not. Right?
Okay. Can you explain what does the arrow stand for? Is it like therefore?
If
okay,
and
if and only if. Okay.
By conditional state.
Okay, thank you.
Geometry, right? Yeah, it means that. See, if you have this, if P is true, then Q is true. This means one direction. P causes Q to be true, but not necessarily the converse, right? But if you do this, then they cause each other. Right? Okay, that's what that means in logic. Okay, number 26 then. Number 26. Wow, can we see the pattern here? Can we put this into some kind of, it's not exactly sigma notation, but at least what's going on? 2, 6, 10. Do you see what that last number in terms of n is? 2, 6, 10. How are we generating this?
Every other even, or every other even.
Say it. Is it for
like 4n plus minus? Oh yeah, that's smart.
Oh yeah. Okay, chance to redeem yourself. The denominator. 5, 8, 11. What are we having?
Like n plus 3 if n starts at 5, or
No.
sorry, no.
3n plus 2.
3n plus 2 is correct. Some people are inherently good at these things, and some people have to think about it a lot, right? Not gonna name names, who's who, but hey, that is quite apparent pattern. Okay. Shall we do ratio test now? Yeah, let's do that. So ratio test, limit as n approaching infinity of, wow, gigantic, basically that thingy, right? 2, 6, 4n minus 2 over 5, 8, 3n plus 2. Good? Okay, the numerator. What is numerator then? Would that be same thing? 2, 6, 4n minus 2, and then you have one more term? What's the next term? Somebody tell me. Oh, somebody's chance to redeem himself. Tell me what the next term is.
Is it like 4
and
4n plus 2?
Wow. Redemption, huh? Okay, the denominator will go up to 3n plus 2, and then we have the very next term, because this is all being multiplied, right? 3n plus what?
5.
5. Redemption is nice, isn't it? So that's what's going on in a ratio test. And then you see everything else cancels. Like these are like factorials in a way, isn't it? These are like factorials, but not going up. This thing is going up by 4, and this thing is going up by 3, but they are nevertheless factorial looking thingies. You know what I'm saying? Do you know what this thing is called in higher mathematics? You want me to mess with you or not? Pi, giant pi, of 4n minus 2, and n starts from, what is it, 1 to infinity. And this thing is pi, and then 3n plus 2, and this thing starts from 1 as well. That's what it is. Sigma is something plus something plus something plus something, right? Pi is something times something times something. So it's like extended factorial. It goes up by any number that you want it to. Not that you need to know that, but it's like comes in handy notation-wise instead of this. You know what I'm saying? Okay, never mind. Like, let's not scare children. No. You don't have to know that. Okay, it'll never be in your high school test. So, do you see that this is just 4n plus 2 over 3n plus 5, just like factorials cancel? Did I write ln instead of limit? Oh my god. I definitely ate too much, didn't I? Where did that ln come from? This is limit. Do you see that? Do you not see that? This is the exact same idea as canceling factorials. And somebody tell me what that limit is. Oh, come on.
4/3. 4/3.
So if the ratio test is greater than 1, what do you say? This is divergent. You don't even have to bother with the alternating series test. It's divergent. Another way of saying it is this term, the sequence inside is growing. You get it? So it will not die down to 0. So this is divergent. It fails everything now. See, ratio test is very nice, isn't it? Okay, so that's 26. Then we are looking at this thingy, right? Erase. Let's do this example. Okay, this is not alternating series, right? Because the numerator will become 2, 1, -1. You know what I'm saying? Let's write this thing out just to see what it looks like. Okay, I'm gonna make it smaller a little bit. When n is equal to 1, you have 1, so you have 2 over 1, right? When n is equal to 2, then you have pi, so this is 0, so we have plus 1 over 2. When n is equal to 3, then this thing becomes -1 now, doesn't it? So you have 0 over 3 plus, and when it's equal to 4, this thing becomes 0 again. Wait, wow, I screwed up. 0 over 3. Well, where was that? When n is equal to 3, this is not 0. Yeah, it is. So 0, -1, yeah. 0. N is equal to 4. This is 0. So we have 1 over 4. 5. Are we seeing the pattern yet? If this is 5, it becomes 2 again. Right? Say yes. 1 over, what is it? 0 over 7. That's the pattern, which you can say is there's no pattern, right? Okay.
Wait, there is. Wait.
And there is kind of a pattern. But how the heck do we
Like,
show the convergence of this or divergence of this? What do you say?
Can we separate them to like 4 series, or I mean the 0 term we can just ignore, right? And we can separate the rest of them.
Yeah. We can have this as a one series and that as another series. You know what I'm saying? And they are divergent in that case, right? Okay, or I guess that's the only way. I was thinking about limit comparison test for the whole thing and compare it to 1 over n. But that limit is horrible, right? We'll never know what that is. Oh, actually, I think I can still make, okay, let's not. It's gonna confuse the children, so let's listen to Josh. This is why I'm hesitant to separate it. Divergent series.
I think I know.
You cannot separate.
Yeah, is it because add them? Yeah, you cannot add them or subtract them, right?
See, that's generally no. Right? So we have to be very, very clever then. Let's be clever. This is the one of the clever plan. Actually, it's not that clever, but hey. This pi over 2 n plus 1 over n is greater than or equal to, what do you say? True? No, it's not even true because of that. That 0 messes us up, right? We were so close. We were so close. That's 0. That thing's 0. Right? We can't do that either. Maybe I regret creating this example. See, this is what happens when you just create an example out of thin air. Then sometimes it's a lot more difficult than you want it to be. God, if there's a square here, this is so much nicer, right? But we don't have square. Heck, we'll just try limit comparison test and try to make sense of it. Okay, because that clearly doesn't work. So we have sine pi over 2n plus 1 over n over 1 over n, correct? That is same as limit n approaching infinity sine pi over 2n plus 1. Good. Say yes.
Wait, sorry, Mr. Kim. I just have a quick question. Can you just technically just do limit of the original thing, and then if it doesn't equal to 0, then we can conclude it's divergent since it doesn't equal to like a finite number or 0. Do you get what I'm saying? Like the last term.
Take a limit of this whole thing, right? It becomes,
yeah, and then
because denominator grows. So eventually, if the top numerator fluctuates a little bit, the denominator being really big will eventually dominate.
oh, so it's still even the plus and minus.
And then this is not an alternating series, so there's like forget alternating series tests, they're all positive.
Yeah.
Right? So this difficult thing is the only thing we have left. Okay? Watch this. So this thingy, right? And it depends on what that thingy is, right? And it could go anywhere between 0 and 2, correct? That thing itself will fluctuate between 0 and 2, right? But we can say this. I will take absolute value of this. Yeah, let's take absolute value of it. Let's say absolute value. So I'm gonna change this to absolute value. And then I can say this is less than 2. I mean, this is what I was trying to avoid, but now I don't see any choice. It's the whole point is this is a finite number. It's anywhere between 0 and 2. You get it? Right? And limit comparison test will still work. as long as this ain't 0 or infinity. Actually, 0 is okay in this case because the numerator is smaller than. No, you have to be careful. Right, but it's some kind of finite number, so it'll still work. Which means, since now it's divergent, right? By integral test, which I'm not going to do, but you have to do it. Do as I say, not as I do. Since that is divergent, this is divergent as well. This is how you want to conclude this thing, huh? Yeah, deep, isn't it? Okay, something that serious ain't gonna be on your test, but we started off, and like I said, if you create an example out of your thin air, this is what you get. Kara.
Sorry, I have a.
Kara, then Josh.
Oh, Josh can go first.
Okay, Josh, go.
Okay, yeah, thank you. But isn't the isn't the limit comparison test the initial condition must be the two series with positive terms?
What? Repeat the question.
Sorry, so we do the limit comparison test here, right? And but the initial condition for the limit comparison test is suppose that summation of a sub n and summation of b sub n are series with positive terms.
Number one, these are positive. But
oh, right.
Better because this is, let's say this is an absolute, the absolute convergence test. You can just always take the absolute value of everything and then call it an absolute convergence test, right?
Yeah, okay.
In this case, it didn't matter because none of these are negative. You know what I'm saying?
Yeah, that's true. That's true. Yeah.
Okay.
And so we can always just like make it less than a finite number. So basically, we conclude that the limit of sine pi over 2n plus 1 has to be 0, 1, or 2, which is not equals to, which does not, wait. Oh, okay. Wait, but it can be 0 technically, isn't it?
Yeah, but it has to be, in order for this to fail, it has to equal to 0 exactly, but this ain't 0. It's like some number between 0, 1, 2, 1, 0, it just goes around.
Okay.
Right, so I think I can still technically argue this is a finite number.
Yeah, I guess. So since it's not always 0, so you can say it's, okay, yeah.
Which means this thingy and our harmonic series, they have about the same kind of growth rate is all my point here, or death rate. These two are about the same thing if n gets really big. Because imagine replacing all of these guys with 1. You know what I'm saying? It's not that much different. It's the whole point of the limit comparison test. Once again, not on your test. So like whoever's watching this video later, don't worry about this one, okay? With this period, fifth period tends to do this a lot. It's like almost daily occurrence of this philosophical higher mathematics, the pi thingy up there, right? This kind of thing, okay? Ignore that as well. Okay, Kara.
On number 8 of the last night's homework on Dropbox, you did like integral and it went to infinity, so you said it was not absolutely convergent, but on the side you also did a limit comparison which went to 1, but doesn't that mean it's divergent? Because if it's not 0, then that means they're either both.
No. That you're kind of mistaking the two. Limit comparison test being 1 is good thing. Ratio test being 1 is inconclusive. The sequence inside being 1 is divergent. You follow? I think I better write that. We'll forget this example. It's so much easier. Limit comparison test, a lot easier than previous example. This is number 8. We're running out of time, so let me just handwrite it instead of copying it. Okay, that thingy. I'm comparing that thingy with, I propose, this thingy. And the reason for that is because I really didn't want to do a which is greater than. Right, so if I do limit comparison test, right, do you see this thingy becomes n approaching infinity multiply, so n squared over n squared plus 1, and which is 1, right? That means these two are about the same thing. And then this, we have done it many times, this is equal to infinity. Right, so these two converge at the same way. So this is divergent, so this is divergent as well. Right, that much is the absolute comparison. I mean, absolute convergence test, because I've taken these alternating signs out. It's like absolute value of this. Good. So this is not absolutely convergent, but we still have to do alternating series tests, because it could conditionally converge. Right, and turns out it does.
Why can't you say they're both divergent?
They're both divergent. Oh, divergent, I just proven that this thing without the alternating sign is divergent. But once you throw the alternating sign back in, this may converge, and in fact it does. I just show you this first part. If you do this, right, this is 0. This will converge. It will pass the second part as well. So at the end, with that, we say this is conditional.
Oh, okay. Thank you.
Yeah. Wow, that was a good question. So it's like this thing getting 1, here is a good thing. In ratio test, if you get 1, that's a bad thing. Here, if you get 1 here, that means it's divergent. You get it? So not these ones are not necessarily the same thing. I mean, if you get 1 here, I guess that's a good news too, because you don't have to do a lot more work. It's divergent there. This thing, not 0, is always divergent in all series. Maybe you should just run with that first. I quickly tell if that thingy dies or not. If it doesn't die, it's automatically divergent in all series. End of the story. Work is done. Good. I think this period
to do the alternating series first, right?
No. Just this part.
No, I mean like the first part of the test to see like automatically if it's divergent.
Yeah. You just wanna just like that. You can tell by looking at it.